In this video, we will be doing math with significant figures. We're going to take the ideas that we developed with counting significant figures to the next level and actually do mathematical operations with them. For our first example, we have the following number: 212.2 plus 26.7 plus 402.09. Now, in all these problems, the first thing we want to do is actually type the problem into our calculator and get a mathematically correct answer. 212.2 plus 26.7 plus 402.09. Typing that into our calculator gives us an answer, a mathematical answer of 640.99. That's mathematically correct, but these in science these values are actually measurements, and so there are significant figures involved in them. We know this first number to the tenths place, the second number to the tenths place, and the third number to the hundredths place. And because this is addition, and you also use this rule for subtraction, you round your answer to the common decimal point, or place, between the tenths, and the hundredths. So the common decimal point is the tenths. We need to round this answer there, and so we record this. The 9 rounds this 9 up, this 9 becomes a 10, that 1 goes over here, and what we get is 641.0. And that is the both mathematical and significant figures correct answer for this problem. Doing the same sort of thing with this problem here, again, the first thing we do, type it into our calculator. 52.331 plus 26.01 minus 0.9981 gives us an answer in our calculator of 77.3429. Mathematically correct. But now these are measurements, now these have significant figures, and now we need to worry about them again. Addition, subtraction, the rule of decimal point. This is to the thousandths place, this is to the hundredths place, this is to the 10,000ths place. Common decimal, the hundredths. So this has to be rounded here. This is 29. That rounds this down. So we report 77.34 as our correct answer. Next problem. This is a problem of addition, but now we have scientific notation numbers. And this is where it becomes more of a problem. I'm only going to cover one method of doing this, but there are two. Alright, the method I'm going to cover, first you take the numbers in scientific notation and convert them back to normal notation. So 2.01 times 10 to the 2 becomes 201. 3.014 times 10 to the third becomes 3014. And now we know we add these together, we get a number, 201 plus 3014. We get a number, 3215. This is addition, so I look at decimal points, or places, sorry. Ones, ones, this is to the ones, that's correct. The other method, which I guess I'll go into briefly here, is to make both these numbers have the same power of 10. So for instance, I can convert the first number to the 10 to the third. You would convert it and you'd end up with 0.201 times 10 to the third plus 3.014 times 10 to the third. And now looking at these numbers, adding the number in front together, 0.201 plus 3.014, gives me 3.215. The power of 10 doesn't change. This is, according to this picture here, out to the thousandths. According to this picture here, to the thousandths. This is to the thousandths. We're good. This would also be my answer. And what I should note is that these two different methods have given me exactly the same numbers. These two numbers are identical. So whether you do it by converting to standard notation or whether you do it by converting to scientific notation, the answer you get should and better be the same. Next problem. This is a problem that involves multiplying a number by, in this case, you may not be able to tell it, but this is a scientific notation number. This number here, the second number, is actually, I recognize as Avogadro's number. And so this is a number that I know is just one number, so I have a scientific notation number multiplying a regular number. So first off, I just do this in my calculator. 0.14 times 6.022 times 10 to the 23rd. I get a number, 8.4308 times 10 to the 22nd power. Now looking at significant figures, this is a scientific notation number. This number here has 4 significant figures. That has 2. You see, the rule with multiplication division is you look at number of significant figures in a number. This has 2. That has 4. You use the least number in your answer. So in this answer, I've got to round this so that it has 2 significant figures. That means round it there. And that means my answer should be, this is 308. That rounds that down. 8.4 times 10 to the 22nd power. This then is the answer to this problem. Moving right along, here is a problem involving 4 numbers, 3 multiplied together, 1 divided out. So, get a number from our calculator. 0.102 times 0.0821 times 273, that quantity divided by 1.01. And when I do that, my calculator gives me an answer, 2.263521386. There's my number. Clearly, looking at these, understanding a little bit about the rules, that is clearly not all significant. I can't report that whole thing. That's way too much. So this is multiplication division. Number of significant figures in a number matters. 3. This has 3. That has 3. That has 3. The least of a bunch of 3's is 3. I've got to round this to that place there so that it has 3, 352, etc., etc. Rounds this down. So I report 2.26 as my final answer. All right. Now, here we've added a complication. Here we have a complication where we have 2 different types of math rules going on, or significant figures of math rules going on. We have multiplication division, but we also have subtraction, 2 very different rule sets. But first, I do exactly what I've always done. Put it in my calculator and get an answer. So the quantity, 6.404 times 2.91 divided by the quantity 18.7 divided by 17.1. I do that math, and I get a number, 11.647275. So there's my number. Now, I need to figure out significant figures. Now, when you approach problems with multiple math steps like this, we need to do order of operations very carefully, very slowly, and determine significant figures at each step along the way. So the first thing I should do is the multiplication on top. So 6.404 times 2.91. Doing that, I get an answer. 18.63564. 4 significant figures, 3 significant figures. Because this is multiplication, this needs to have 3. This would have to be rounded to there. And now this is divided by 18.7 minus 17.1, which according to my calculator is 1.6. Tenths place, because this is subtraction. This is tenths place also, which it already is, which is okay. So effectively what this is saying I should do is 18.6 divided by 1.6, which tells me 3 significant figures, 2 significant figures. Because this is division, my answer needs to have 2 significant digits. Now, I don't do this step. Don't do that on a calculator. You don't want to use rounded numbers to get a final answer. You want to use the true value from the calculator for the actual math and then just round it appropriately. It needs 2. I've got to round this there. That's a 6.4. That rounds that up. So I report this out at the end of the day as 12 as my final answer in this case. Two significant digits, you see. Okay. Now, here's another problem, compound math again. I have some additions, I have some divisions. Alright, but once again, first step, always put in your calculator, get a number. 2.526 divided by 3.1 plus 0.470 divided by 0.623 plus 80.705 divided by 0.4326. Doing that in my calculator gives me an answer, 188.1272741. Alright, now what I need to do is I need to look at each step along the way, order of operations, and figure out significant figures that way. Now the first thing I should be doing in each case is the division. So the first term, 2.526 divided by 3.1. My calculator tells me that this will be 0.81483871. This is division, 4 significant figures, 2 significant figures. That would have to be rounded there. Right to that place there. Now, next one, 0.470 divided by 0.623. Calculator spits this out as 0.7544141125. 3 significant figures, 3 significant figures. This needs 3. That would have to be rounded to that place there. Plus 80.705 divided by 0.4326 gives me 186.5580213. 5 significant figures, 4 significant figures. This needs 4. This would have to be rounded to that place there. Now if I look at my underlines, I can see where I need to round this. Hundredths, thousandths, tenths, because these are all added. Which means I need to round my final answer to the tenths, so I come back up here to my real number. I need to round to the tenths, which means I need to report this as 188.1. Correctly rounded for significant figures. This is a division problem with scientific notation. But again, we start off the same way. We do it in our calculator. 2 times 10 to the 6 divided by 3 times 10 to the minus 7. And so my calculator spits out at me 6.666666667 times 10 to the 12th power. Now, for rounding, this is just division. And remember, the times 10 to the whatever, those don't count for significant figures. I only look at the first number. So I have 3 significant figures, 3 significant figures. This needs 3. Round this there. 666, that rounds this up to a 7. So what do I get? I get 6.67 times 10 to the 12th power. So the power of 10 does not change. I just round off that first number. Alright. Finally, here's more of a wordish problem. I want the average of 4 numbers. 9.5, 4.1, 2.8, and 3.175. Now, when we write this out to do a average or a mean, what do? We just first add up the numbers. 9.5 plus 4.1 plus 2.8 plus 3.175. And then you divide that sum by how many numbers you added, which is in this case 4. And that then gives you the average or mean. So 9.5 plus 4.1 plus 2.8 plus 3.175, quantity divided by 4. And I get a number out of my calculator, 4.89375. Now, significant figures. Once again, order of operations, do the top. The top part, when I add up 9.5 plus 4.1 plus 2.8 plus 3.175, I get a number, 19.575. I'm going to divide that by the 4. Now, this top number, however, I have to deal with significant figures. This is addition. Ones place, ones place, ones place, thousandths place. This needs to be rounded to the ones place. So this needs to be rounded right there. So really what I have effectively is 19.6 divided by 4. Now, before you jump in and start rounding your answer so that it has one significant figure, because remember this is division, that has 3, that seems to have 1, but it doesn't. It doesn't actually have 1. We have to remember back to our rules of counting significant figures, and that is there are 2 kinds of perfect numbers. Perfect numbers are numbers that have unlimited significant figures. There are 2 kinds. One of them is when we define it by definition that way. That is to say, if I have 1 inch, which has been defined as 2.54 centimeters. What we're saying is that this is exactly 1 inch and exactly 2.54 centimeters. These have unlimited zeros after those numbers. So this is 1.00000 out to infinity, 2.540000 out to infinity. These are perfect numbers. They have unlimited significant figures. But the other kind of perfect number that has unlimited significant figures are numbers that are counted. If you have 12 pencils in a box, you have exactly 12. Therefore, that 12 is a perfect number. It's 12.000 out to infinity. Well, this 4 on the bottom came from counting how many numbers we're adding together. We're adding 4. We have exactly 4, which means this is a perfect number. So this doesn't have one significant figure. It has unlimited significant figures. So this 3 significant figures versus unlimited, 3 is the smaller. I have to round my answer so that it has 3. I must round it to that place there, which means this number gets reported as 4.89. And that then is the correct final answer. You have to be careful from time to time of making sure that a number is not perfect. We will cover this more. We'll see more of these examples of these perfect numbers, especially the ones by definition, in the next video on dimensional analysis.